the stuff that was in that first section, as well as stuff that you'll see in section 7 or 6, I think this is, or 7, 6. I forget what chapter we're in.
12.
7 and 7, 6. It's a little bit of a mixture of both. So what I was doing was just pushing it. That's what I do. Aside from number 2 on the first page, it should not have been that difficult. What you had to do a couple of times was just move some stuff over, square both sides, you get binomials, you got to do a little bit of factoring, and set things equal to 0 to solve for zeros, providing you're using an answer sheet.
I've never heard of those.
I had no doubt. Other than that, other than number 2, this first page should not have been horrible. Okay? When you get to the second page, this is where I kind of let it up to you guys a little bit more. Remember, I wrote two examples, I think, up on the board before we left yesterday, about how you're working with the exponents, how you undo fractional exponents. In order to undo a fractional exponent, you got to go back to think about the most basic idea. When you have, what was it, x minus 2 equals 6. If you were going to solve that problem, what's the first thing you had to do?
Square.
You squared both sides. Now that you guys know all right, we have to rephrase that. What is the square root in terms of an exponent?
Half.
It's half, isn't it? So isn't this the same thing as saying x minus 2 to the half power equals 6? And what did you do here? You squared both sides. What's the reciprocal of 1/2? 2 over 1. If this was the third power, cube root, what would you do? You cube both sides, right? The nth root of 3 written as a fractional exponent is 1/3, isn't it?
Yeah.
So you're just using reciprocals. You use reciprocals to undo fractional exponents because you're multiplying them to create them into powers of 1. So I gave you that second page there to see, with those a couple of quick examples there, to see if you can figure your way out here. Obviously, when you get to number 11, divide by 3, and what'd you do? You fourth it. Okay, you don't forfeit, you forfeit it. Yeah. Here, you've got, basically, this is the cube root of r minus 24 is 4. How do you undo a cube root?
Cube it.
You cube it. Now, as you get into some of the more funky looking ones, like number 15,
You 2/3 it.
you wind, at the very end, you're going to wind up 2/3ing it, but you have to do all the other algebra that you work backwards from that you've done in the past. It's just a longer multi-step problem.
That one wasn't bad at all.
It isn't. When you start thinking about it, you have 2 times junk is going to equal 1024. Divided by 2, you wind up with
512.
junk is 512. And then you 2/3 it. When you 2/3 that, you have 1 minus 13x will be, cube root of 512 is 6. Is that right? No.
6, I got.
What's the cube root of 512?
Oh, 8.
Oh, 8. Thank you. Oh, 8. 8 squared is?
64.
Add 1, divide by negative 13, you get negative 5. So what you're doing here is you're working with the reciprocals to undo those things. John?
Okay, so I've been like, you know how like it says in 2 over 3, like 3 over 2?
Mhm.
Okay, so you know how in, like earlier in the chapter we learned like the say like
Yeah.
this one? I've been doing that and like just
Working it the long way?
yeah.
That's fine.
Is that okay?
It's okay. It's just a longer way. And you'll find out, as we get into more and more of these, it's going to be easier to use reciprocals to be done.
Okay.
Okay? Yeah, Clay.
So I used the reciprocal because I wrote like 1 minus 13m. I wrote a square around that,
Yeah.
and then wrote the cube root and everything. And then I just did it to the other side and ended up like, do we have to do
The
this?
easiest way to do it. Because you're getting the variable by itself with the power of 1.
But
When you multiply two things, when you multiply reciprocals together, you always get 1. That's how you undo those fractional exponents.
okay.
All right, does that make sense? And that's why, like I said, I was leaving it out there with these couple of quick examples just to see if you guys can get through them. Yeah.
You also reviewed number 17 because I tried that a lot. Just didn't have to.
I'll briefly talk about it because I want to go and get going into a lot of the other stuff. 17, you have to work with the fraction. Just use your fraction button on your calculator. When you use your fraction button on your calculator, you type in the 2188 over 243, use the alpha y equals, subtract 9 right away, hit enter, divide it by 3 right away, hit enter, Raise that to the negative 2/3, hit enter. Subtract 9, hit enter. Divide by negative 3, hit enter. You're done.
So you can do that all?
Yes, sir.
Okay, thank you.
Every one of those things works in the calculator. You just have to do it step by step, just like you would normal order of ops. It's just working with more ops.
Okay, thank you.
So this one, 13, if you do it like, it has a negative, right?
Yeah.
So then this is negative 2.
Yeah, you're just raising it to the negative power, and you can do that in the calculator, and it automatically does it for you. And remember, when you're putting something in a negative exponent in your calculator, all you have to be able to do is, well, I was doing one here. Let's say it's 3125 raised to the, if you want to go to the 2/5 or 3/5, you just put into the exponent there, parentheses, 3 divided by 5. And you can type that fractional exponent just like that, and it works. Except for the fact that the little boxes there, but it'll work.
And for the opposite reciprocal, if the denominator...
There's no opposite reciprocal, just opposite. It's just reciprocal.
If
Excuse me.
the denominator is positive, then it's plus or even, sorry. If the denominator is negative, then it's plus or minus.
With fractionals? No, fractionals is the same. You're not going
But
to,
for the answer, say like...
because you factor out, you might have, some of those you might wind up with 2 answers. Because when you simplify it through, you might wind up with something different. But yeah, and then the last group is leading you now into what we've been. The last grouping here is what's getting you into the stuff that we've been working on before. When you had power to power, or when you had anything with your exponent rules, you think back to your exponent rules. You had same base, different exponents, and you were multiplying them together. What did you do to the exponents? You add them together, so it would be a to the m plus n. So if it was x cubed times x to the 4th, you get x to the 7th. Okay, so now it's x to the 3rd times x to the 4th. You just add your fractions.
1/6.
Yeah.
Hey, good job. Oh, that
Common
makes-
denominator.
That makes sense.
You just adding fractions. The rules don't change. The rules aren't going to change at all. You're just putting fractions in.
Wait, how is 6 a common denominator?
It's not. It's 12.
And to get 2 over 12, and then 2 over 12.
Yeah. So,
Oh,
4 12s, 3 12s. Oh, it's 7 12s. What'd you guys want?
Yeah.
6.
Never mind. Don't listen to me.
Yeah, I was going to say, wait, what a sec. Yeah.
Wait, what a sec.
So you want to do like that? Right.
Good,
Yeah. So all those exponent rules that we've done in the past, as far as same base, different exponents, you're multiplying, you add them. Same power to power, you multiply. None of those rules change. They just become fractions, guys. So save that. Oh, let me show you number 2 real quick, and then we're going to save this and build out over the next few days.
what is the plan tomorrow doing in the half day?
Math. Not changing anything. We've got 28 minutes, and we're going to do math.
One for fractions still always work.
What's that?
Like one for fractional, one is still
Yes. In this case here, you've got two radicals on one side and nothing on the other. We all agree that at some point in time you have to square both sides to get rid of radicals, right? Now, what I'm going to do here is, in order to do this cleanly, this is kind of the weird way, move one of them over. So I had the square root of 1 minus 2x is the square root of negative 3 minus 7x minus 2. You okay with that?
Yes.
All right. Square both sides. Now, the stuff on the right, can I say it's the same thing as a minus b quantity squared?
Yes.
Isn't that a squared minus 2ab plus b squared? Does it change with the radical in it? Nope. So you get 1 minus 2x is negative 3 minus 7x minus 4 root negative 3 minus 7x plus 4. I FOILed it out. The trick in this problem is that you're going to wind up having to square both sides twice. All right, this is a difficult solve. I didn't expect you to get it. Good, if you got it, that's awesome. I don't expect you. I expect you to be able to solve the rest of that problem, albeit you might have been swearing my name more than normal. But that's okay. I got big shoulders, I can deal with it.
Doesn't matter which root we put on the other side to do too.
It doesn't really matter. I just moved down one because it would move from a negative to positive, just a little bit easier to work with. Now, on the right-hand side, does everybody agree that it winds up being 1? The negative 3 plus 4 is 1?
Yeah.
Is that okay?
Yeah.
Now, I'm going to add 7x, and I'm going to subtract 1 to the left side. Okay with that?
Yes, sir.
How do I move the negative 4?
Divide.
Okay? So these two drop out. How do you undo squaring? Or undo square rooting,
Square it.
excuse me. Square it.
Where'd the 1 go?
I just erased it. I subtracted to the other side. That's 1 minus 1.
No.
All right? Square root of junk squared is? 5 squared
25x squared.
over.
16.
You get 25x squared over 16 is negative 3 minus 7x. Where? There was. Negative 4 times negative 4 squared is 16. Okay. Now, at this point, what I'm going to do, I'm going to multiply everything by 16, get rid of the fraction, and after I do that, I'm going to set aside equal to 0. So I'm going to multiply the right side by 16 and subtract it all over to the left. 25x squared plus 112x plus 48 is 0. Now I have a factoring problem that I don't want to do because those are big numbers and it looks hard.
Quadrant formula.
You can use quadratic formula, absolutely, or oh, you want a complete square on that one? Good luck. Look at those fractions.
Don't try it. It didn't work. I tried pretty much everything, but I didn't.
You have a 0 at negative 4. Using the table function on my calculator with that quadratic, I get negative 4 for one of my zeros. But upon looking at the graph, you'll notice that it also crosses here, a non-integer value. But your calculator has this button called Calculate, and in that option it says 0. So you can calculate your zeros. Similarly, I use to calculate maximums and minimums, left bound, right bound. When you do that in your calculator, you get another 0 located at negative 0.48. So this quadratic had two possible zeros, negative 4 and negative 0.48. You check for the extraneous solution, you find that negative 0.48 doesn't work. And that's how it works. This is an honors algebra 2 question. That's a damn good question.
Does that mean you're going to put it on?
It is a terrible question.
Yeah, quadratic formula. If you didn't want to, if you didn't want to jump into your table function here, because it's a crapshoot, you don't know off the top of your head if you're going to get a clean 0. I just go that way first, just because it's fast to see if I get a clean 0. Quadratic formula, by all means, you're going to get the same idea where you do your plus minus. You'll get both those two values. One of them was probably just came out as a fraction, 24 over 50, so it'd be 12 25ths.
It just got really weird.
Yeah,
so
it's
just
negative
assumed
12
it was
25ths.
Extra drinks.
Yeah,
I
extraneous.
just kind of canceled it out.
I can't just, I just can't cross things off.
Just assumed it wasn't working.
Don't assume.
I'm going to assume all I want.
So save this one. We're going to build out of these last couple of pages over the course of the next few days. So let's look at 7-2.
So it's negative 112 minus.
And like I've shown the rest of the classes, I have to show you them. So, like I was saying, your properties of the exponents, these properties aren't going to change, guys. You know all of these properties of the exponents. all of these properties are the same as they were a couple of chapters ago in working with them. None of these changed. No, these are all the same you've always worked with. What's going to change off of this now is we're just going to work with exponents that have fractions in them. That's it. Instead of adding 2 plus 3, you're going to add 1/2 plus 1/3. That's all it is. Instead of multiplying 3 times 7, you're going to multiply 2/3 times 4/5. That's all it is. I know. But that's all this stuff is, guys. None of the stuff that you have done in the past change as far as what it's going to look like now. We still do the same exact things. So let me show you just a couple of quick examples here of how fast and how easy this stuff goes. It is rad. Right, okay. You can watch the entire movie on YouTube.
I'm not going to do that.
I don't want to.
I'll do it if you give me extra credit for it.
No, not happening.
What if you write a report on it?
No, it's still not happening.
Show up on a bike.
You'll feel better about yourself.
Can you ride in this class on bike?
No, I won't. If I spend however long watching that movie, I will feel so much worse about myself.
So, like I was saying, I just want to show you a few couple examples here. What I'm looking at here, I got 5 to the 2/3 times 5 to the 4/3. Do they have the same base? Yeah, 5, right? Different exponents. You're multiplying them together. What do you do to the exponents?
Add them.
You add them.
Dang it.
So this becomes 5 to the 6/3. What's 6 over 3? So it's not power to power. Power to power is when you multiply. Power to power is when you had to distribute through, when you had x to the 3rd to the 4th power. How do you mean 25?
5 times 5.
Oh, I'm sorry. Okay, all right. I knew it. Now I understand what you're saying. I'm sorry. When you did this, it was x cubed times x to the 5th. X was the base, wasn't it?
Yeah.
So this was just x to the 8th. Instead of this being x to the 2/3, x to the 4/3, it's 5s. The 5 value is the base. Does that make sense now?
Yeah.
The base value, it doesn't matter. As long as it's the same. Yeah, as long as it's the same, you can do all the properties whole. All right? When I look at the other one, I have 3 to the half in the numerator and 3 in the denominator. Does the denominator have an exponent?
Yes.
What?
1.
It's got an exponent of 1. It has an exponent of 1, but yet the numerator exponent is in terms of 1/2.
It's going to be...
Not 1 over 1, I want to use 2 over 2. 2 over 2. I want to rewrite this as 3 to the 1/2 over 3 to the 2 over 2. You okay with that? Who wins in the battle of war? 1/2 or 2 over 2? 2. So now it becomes 1 over 3 to the half. You okay with that?
Wait.
Oh, okay.
If you're 3 over 3, doesn't that simplify to 1?
Did it simplify when it was x to the 5th over x to the 13th? The x's disappeared, just had 5 over the 13th?
No.
Because the value of 3 is what? It's the base. Okay? Yes, ma'am.
But didn't we just like when we were going over it, didn't we like switch the fractions so it would be like 5 to the 2/3 would have been only 5 to the
No, that's if you were undoing it to solve for equations. When you flip things around.
Is that the final answer?
No, not yet. We'll get to what it is. I'm
It's
just
going to be
thinking.
1 over 9.
No. Now, we'll get to what this actually. What does 1/2 power mean again? Isn't that 1 over root 3?
Oh, you have to rationalize.
And you have to rationalize, okay? We'll come back. For right now, I'm just looking at playing the game of war. We'll come back to worry about the rationalizing of that later. All right?
Like how later? Like later today?
Couple
Later
minutes.
next week?
And this last one here,
Later next
hey,
week.
I'm just gonna. You guys can complain all you want. I got a lot further earlier, so you gotta just maybe stop talking as much would be helpful. 7 to the 2/3 raised to the 5/2. Remember, this is mirroring the same idea as power to power. When you have power to power, what do?
Multiply.
Multiply. Now, when you're multiplying fractions, remember, you're multiplying straight across, numerator to numerator, denominator to denominator. Here you get 7 to the 10 sixth. And can you simplify 10 over 6?
Yeah.
What do you get? 5/3. And there's your result. We're just rewriting it in terms of the exponents. Okay? When you're working with fractional exponents, if they start with fractional exponents, end in fractional exponents. If they're working with it in terms of roots, if they start roots, you end in roots. Which means you have to remember a couple of properties of roots. And it's very easy to remember. What's that?
2 root 3.
2 root 3, very good. How did you figure that out?
4 divided by 3, 4, the root of 4 is 2, so that goes on the outside.
What you did there is you broke the square root into different parts. You broke it into the square root of 4 and the square root of 3. So both of those roots have the same nth root. Are both of those the same nth root?
Yeah.
You say that? They're both square roots. So you guys did this before without this value of n there. So if I wrote something out as, maybe, so then the final has to be 2 root 3, okay. Let me show you the book. If I do it this way, where it's the square root of 2 numbers, the nth root of a times b, you can split it apart as the nth root of a times the nth root of b. It's the same exact thing. It's identical to what you did before. Okay? It's absolutely identical. Let me show you. If you have something like this, I think an easy one to set up for.
Is this something we should write down?
Well, you know the property already because you've done this. It's just a matter of the example. I'll show these. And then same thing with the quotient one. You take a fraction. If you work with a fraction of a root, you simplified it to both numerator and denominator, and you simplify it out. You've done that. And then you'd rationalize. And like I said, we'll talk about rationalizing here in a little bit. It's a little bit weirder when you rationalize with fractions as it is with the square roots as we did before. Slight twist. All right. Now, product property. Are those both the same nth root? If they're both the same nth root, what can I do to the stuff underneath the radical? Multiply them together. So I get 3 root, or excuse me, not 3, the cube root of, what's the cube root of 64? You're still on terms of squares. All right, and this has come up also throughout the day today. Cube roots. You should know your cube roots through 6s. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and 6 is 216. All right? To be honest with you, anything above that, you start to want to use the calculator. I try to keep all my non-calculator stuff within those values without being too crazy. Okay? So notice how we're able to do that by simplifying stuff out. Works the exact same way when you're dealing with fractions. Do these guys have the same nth root? Since they both have the same nth root, I can rewrite that as one giant fraction. I can rewrite that as the 4th root of 162 over 2. What's half of 162? 81.
Thanks, Thomas.
So you get the 4th root of 81, which is 3. Okay. Oh, some of these, I mean, what are 4 numbers that are the same that go into 81?
I don't know. I messed up.
I mean, it can't be, it's not going to be 5. It's not going to be 2 because it doesn't end in an even number. I mean, basic ones. You should know 1. You should know 1. I hope you know 1 to the 4th power. You should know 2, 3, and 4.
It's 4,
That's
right?
fine.
That's
Yeah,
fine.
it is, man. It's awesome. We're air 5, man. We should go this. Which means
What that joke was. Okay.
you don't remember me. Well, I remember this. She's just trying to forget. Now, going back to the square root of 12, remember how we broke it out to perfect squares? 4 and a 3. So you get 2 root 3. When you break down cubes, you're looking for perfect cubes. So your perfect cubes, like I said, 8, 27, 64, 125. So does 8 go into 54?
Yeah. No.
No, you're good. Does 27 go into 54? Yeah.
Yeah.
How many times?
Twice.
Twice. So I can rewrite this then as the cube root of 27 times the cube root of 2. It's the cube root of 27. And you simplify radical the exact same way as you used to with the square root. Now, instead of looking for 4, 9, 16, 25, 36, and so on, you're looking for 8s, 27s, 64s, 125s. It's a little bit less of a pool to comb from, okay? It's a little bit less of a pool.
And we just leave the cube root?
Yeah, because can you simplify the cube root of 2? No. So you just leave it right now as that nth root like that. Just like you did with the square root of 12. You just left it like that, we went there. Okay? I'm going to go back to rationalizing tomorrow, but I want to show you, because it gets weird, and I don't want to freak you out too much.
Yeah. So with square roots, you can do like find the factors of numbers.
Mhm.
Can you do that with the cube roots?
Yes, you can. You can do the same thing. And, I saw some people doing that. I saw Izzy do that today on her homework. When you do that, if you're looking to factor this completely into their primes, you get, what is it, 2, 3, 3, 3.
So instead of 2 goes in, 1 comes out, it's 3 goes in, 1 comes out?
Yeah.
Okay.
Yeah,
I think
it's exactly what it is. Because I think that's right, correct? Yeah. See how you've got a bunch of 3? All of them can come out. Yeah, you'd have to have 3 of them.
And then like
3
so
of
on.
them. Yes, you have to have 3 of them.
Okay, that makes more sense.
Yes. All right? That's exactly what you're doing.
Okay.
If it's easier for you to do it that way, I have no problem with it. Okay? I have no problem with that. Which leads you to be able to do stuff like this. Adding and subtracting. Combining like terms. That's all that is, right? When you had combined like terms earlier, what was the basic rule of that? You had to have same base, same exponent to add, same base, same exponent to subtract, correct? Okay. Now, in that first example, what's my base? What's my exponent? Are they the same?
Yes.
All right, now hold on tight. 7 plus 2.
14.
Nice work!
9.
Where are the trees?
I say it's obviously 3.
Here's the joke.
You in the visual?
You okay with that?
Yeah.
I just made that up just to help show why this works. Same thing, right? It came from here. Does that make sense? I was just showing why it worked. Since it was the same base, same idea if it was 7x squared plus 2x squared, you get 9x squared. You all right?
Yeah. I'm good.
You're going to be okay. No, she's not. Yes, ma'am.
Okay, so like, do we leave it at that?
Yeah,
And
can
then-
you do anything?
Yeah, wait,
No,
you
but-
can't.
I'm kind of like, having to learn like how to solve all this.
It didn't become 9x squared, did it?
No.
No. You're combining like terms. It's this, these properties here, Tom, are the same here. It's the same thing. It just looks different.
That's really that's final. I think it's
Yes. And like I said earlier, you don't need to rewrite this in terms of roots. If you start in fractionals, in fractional exponents, keep it in fractional exponents. You start nth roots, leave them at nth roots. Now here, they don't have the same base, do they?
No.
They don't, but what do they have?
The same.
The same nth root. So could I make this into a root with a base of 2? 8 and 2, isn't it?
Yeah.
What's the perfect cube root that goes into 16? 8. So this is the cube root of 8 times the cube root 2, which is 2 cube root 2. Minus, now I'm going to do something a little bit different here.
Okay, that makes sense.
Oh, because you get a distributing up.
Okay.
So then would it be, so it's cube root.
Now, what I've done here, I wanted to simplify this to create it to have the same base with the same nth root. We already have the same nth roots. It's 3. You would drop if you weren't using it. And what I want to do is change that 16 to have it a base 2. To get that base 2 here, I'm going to simplify it out. 16 is 8 times 2. 8 is a perfect cube. Cube root of 8 is 2. So the cube root of 16 simplifies to 2 cube root 2. Then I'm subtracting cube root 2. Now the reason I put the 1 in front is because most people at this point screw something up. For example, let me show you this. What's 2x minus x? X. Good. So what's 2 cube root 2 minus 1 cube root 2?
Cube root 2.
Good, you didn't screw it up. Most people will just say it's 1, or most people will say it's 2, because they think that these just drop out. Remember, when you're working with these as far as combining like terms, you're treating it like you used to with just variables. It just so happens now your variable looking things are nth roots or fractional exponent roots. Okay? Yes, sir.
What happens if it's like, you know the pack you gave us?
Yeah.
And you already have like, it's all exponents. How can you substitute? That seems really confusing.
You're doing the same thing, man.
But like, how can you substitute, pretend there's an x there if you're multiplying 2 x's instead
When
of...
you have the same base, different exponents, you add the exponents.
Okay.
Same things it used to be, just with fractions. You didn't get anything numerically yet. You haven't gotten any of that yet. All right? Last one.
Screw that.
You can not do all of these things if you're going to say screw it. All right? The last example always works out to be the easiest for today.
I'm not coming to class tomorrow.
Is it,
Hold on. What's the cube root of 125?
5?
3 goes into 6 how many times? Any left over? I'm not even bothering showing you the rule. I'm just showing you the shortcut. Watch. Do you agree that this is the same thing? Oops. Do you agree that's the same thing? All raised to the 1/3 power. 1/3 power, you distribute down. So you have 125 to the 3rd, and then you have y to the 6th to the 3rd. Isn't that power to power? When you multiply together, what's 6 times 1/3? 6 over 3, otherwise known as 2. So you can also do stuff that looks like this. What's wrong one? Oops. Oh, sorry. It's just a little bit. Now this one. Take a deep breath. Trust me. I haven't screwed you up yet. At least
Yeah, you have.
Yeah.
Pretty bad.
I tried.
Thank you for that.
Oh man, we're running real short here. All right, this real fast. What's the cube root of 8?
2.
2 x squared.
All right, 3 goes into 6. How many times? 2. 2 come out. Any stay in?
No.
No. So here's how I'm just going to make a little cube root just in case. Does 3 go into 2?
No.
3 goes.
Does 3 go into 1?
No.
What's the cube root of 27? 3. So this becomes, oops, sorry. I have a 3x because it's already out there. 3 goes into 3 how many times?
1.
So 1's got to come out. 3 goes into 2 how many times? None. And I just have that left over of y squared z. So this becomes 3x squared. What's 3x squared plus 2x squared? That's the easiest stuff of the whole section. We'll do more and more and more of that. It is, isn't it? Section 7.2, the rationalizing is usually what's the toughest, this one. Page 411, I believe. I want you to do numbers, I think it was 24 through, let me steal your book real quick. I'm trying not to do the rationalizing ones right off the bat. Let's go 22 through 54, but don't worry about, yeah, evens. Don't worry about, I think it's 46 and 48. I think those are the two with the rationalizing. There might be another one thrown in there they have to rationalize. We'll worry about more of that tomorrow.
Okay.
Remember when you can't have roots in the denominator? Like 1 over x squared became, bless you, root 2 over 2. It's the same thing with the nth roots, but instead of it being, it gets a little bit messy. So I need to give it a little bit more time. So. Yo!